So today we're going to be having a look at rate of change. And just as a reminder, rate of change is generally to do with two different variables changing and the rate at which they are changing with each other. So we're interested in some kind of gradient dy dx, something like that. Depends on the question. So let's read the question and see if we can figure it out. So a 5-meter ladder has its upper end leaning against a vertical wall. So this must be the ladder here. And its lower end on the horizontal ground. The ladder makes an angle theta, radians with the horizontal ground. The lower end of the ladder is slipping away from the wall at a constant rate of 0.2 meters per second. Consider the instant that the base of the ladder is 3 meters from the wall. So, you could imagine that as the ladder slides down, the base moves away down here, so then the height of the ladder shrinks a little bit. So we want to understand the relationship. So let's start labeling our variables. So x is going to be this horizontal distance, y is going to be the vertical, and we can use Pythagoras' theorem to write x squared plus y squared equals 5 squared. And we can rearrange this for y. Now we've taken the square root. In this case, we're only interested in the positive y because this is a distance, and it doesn't make sense in this context for the y, the height of the ladder, to ever be negative. So we're only interested in the positive root. Alrighty, so that was just algebra up to here. But let's actually think about what the question says. Determine the speed at which the top of the ladder is descending. So we want to know dy, the change in y, but not compared to the change in x. We're actually interested in it compared to the change in t. Now this becomes a tricky question, right? Because we're not exactly sure how to work this out. We don't have a relationship between y and t. We've got a relationship between x and y. But we know from chain rule that if I can work out the derivative of x, I can multiply that, the derivative of y, I can multiply that by the derivative of x with respect to t, and that would actually work out. Now, the interesting part is that we actually know what dx dt is. It's actually given to us in the question, 0.2 meters per second. So we know dx dt is just 0.2, right? Because that's what it says. The lower end is slipping away from the wall at a constant rate. So all we now need to work out is this, in particular, at x equals 3. Because we know that this is just a constant. This part here is just a constant. It's going to be that the whole time. So if we're going to be taking the derivative of y over here to get dy dx, well, the first thing is let's rewrite it so it's got a power. Square root is the equivalent of to the power of a half. Now let's go through and derive it. Dy dx. Bring the half down. Half minus 1 is negative a half, multiplied by the derivative of the brackets, which is negative 2x. Now we can clean it up a little bit. Half times negative 2x is negative x. And 25 minus x squared to the power of negative half, well, is better written as negative x all over, and then the square root of 25 minus x squared. I'm just cleaning up this a little bit, because the next step I'm going to do is substitute in when x is equal to 3. So when x is equal to 3, dy dx is equal to negative 3 all over the square root of 25 minus 3 squared. 25 minus 3 squared is 16. Square root of 16 is 4. And I get negative 3 on 4. So dy dx is negative 3 on 4. And dx dt is 0.2. So let's finish the problem. Dy dt is equal to the change in x times the change in x over the change in time. And I know that dy dt is negative 3 on 4, and dx dt is 0.2, which could be better written as 2/10 or 1/5. And when I multiply these together, I get negative 3 on 20. That means that since our units so far have been to do with what? Second and meters, this is meters per second. And the fact that it's negative means that the ladder is slipping down the wall. So the ladder slips down the wall at 3/20 of a meter per second. So it's going down at that speed. Alrighty. So the second part asks us to do a similar thing, but to do with the rate at which the angle theta is changing. So let's have a look at that. So for part B, we're interested in the rate at which the angle changes with respect to time. Once again, let's use the same trick we did before. That means we're interested in d theta dx multiplied by dx dt. Problem is, d theta dx is going to be hard to work out. But we've got a trick for that. So let's not worry about this too much just yet, but let's first of all think about this. Well, in this particular case, have a look. What's the relationship? The right angle's here, and these are our two other ones. Well, this is the adjacent, and this is the hypotenuse. What deals with the relationship between these two? Well, it's cos of theta is equal to the adjacent over the hypotenuse, or in this case, x over 5. Now, at this point, you might be tempted to do something along the lines of theta is equal to cos negative 1 of x over 5. But doing this will stuff us, because we have no strategies for deriving cos. Okay? Sorry, we have lots of strategies for deriving cos. We have no strategies for deriving inverse cos, because inverse cos is not the same as cos to the power of negative 1. These are not the same thing. This cos to the negative 1 is actually arc cos, which is the inverse cosine function. So this is an important notational difference here. So we cannot take the derivative of this. We have no strategy for this. But instead of trying to find d theta dx, what if instead we found dx d theta? Well, I think that could work. Because if we then inverted that function, meaning putting it 1 over, we'd be able to work it out. So let's not do this silly step. That was a mistake. Let's instead solve for x. Well, x would be equal to 5 cos of theta. And I could actually work out dx d theta quite easily. Right? Cos goes to negative signs. We get negative 5 sine of theta. No need for chain rule. This is a direct solve. But I didn't want dx d theta. I wanted d theta dx. So I need to invert it. And to invert something, we just put it 1 over. Bring the negative to the top. And there we go. But remember, we already know what this is from the first part. It's 0.2. But one problem. We still haven't finished with this. The other problem with this is that we're interested in what this is when x equals 3. We actually don't know what theta is when x equals 3. So we actually need to go back to this part here. So let's solve for this. What's cos of theta when x is equal to 3? All right, well, when x is equal to 3, we get cos of theta equal to 3 on 5. Apologies, we're not doing that substitution. So we worked out in the previous question that when it's 3 meters, we end up with this magical triangle here, right? 3, 4, 5. That's what we worked out in the previous part of the question. And so what we want to do is we want to work out what's sine of theta. Well, sine is opposite over hypotenuse, which we do know. It's just 4 over 5. So sine of theta is equal to 4/5. Substitute 4/5, well, into here, or into here, and then just invert it, but we'll substitute it into here. So we get d theta dx is equal to 1/2 over 5 times 4/5. 5 times 4/5 is just 4. And so we get d theta dx is -1/4. And from the previous part, we already know what dx dt is. It's 0.5. So we get -1/4 times 0.2, which again is 1/5. And we get -1/20. And in this case, what's the units going to be? Well, it's decreasing. So the angle is decreasing, that's what the negative means, by 1/20th radian per second. Right, because we're measuring theta is in radians and t is being measured in seconds. So d theta dt meaning radians per second. Alrighty, and that is some rate of change. Some pretty tricky stuff happening in here. So good luck working out some of this stuff. I'll see you in the next one. Goodbye.